Alright, we have a lot of stuff that we've learned about ions. And I wanted to do a video here to kind of recap and provide more examples of how to work out things like the number of electrons in an ion or the charge of an ion, the Lewis structures and the bonding and all. Remember, when we're dealing with ions, we're dealing with either metals or nonmetals. When ionic bonding takes place, we have to have a metal, we have to have a nonmetal. Metals are the things to the left of the metalloids. Typically, they have 1, 2, or 3 valence electrons. Group 1A has 1 valence electron. Group 2A has 2 valence electrons. Group 3A has 3 valence electrons. Metals in general have low ionization energies. Ionization energy is the amount of energy it takes to remove an electron from an atom. By saying metals have low ionization energies, what we're saying is it's easy to remove their electrons. It doesn't take much energy at all. They have low electron affinity. Electron affinity is the amount of energy that is lost by an atom when it gains electrons. What this is saying is they don't lose much energy if they gain electrons. In other words, they don't become much more stable when they gain electrons. When you combine these two trends together, this is the reason why metals lose electrons. When a metal loses electrons, it throws the protons and electrons out of balance. Typically, in an atom, you would have an equal number of protons and electrons, an equal number of positive and negative charges. That would cause the charges to cancel out and the atom to be neutral. Because we're losing electrons, there will be more protons than electrons. This will throw that charge out of balance and make them positive ions. Positive ions are called cations. Nonmetals are pretty much the opposite. We find the nonmetals to the right of the metalloids. The ones that are involved in ionic bonding are those in 5A, 6A, and 7A, having 5 to 6 valence electrons. There is a nonmetal in 4A. It's carbon. It doesn't really do ionic bonding. There are nonmetals in group 8A, but they already have 8 valence electrons. They're already stable, so they don't do bonding. The nonmetals we're concerned with are in groups 5A, 6A, and 7A, 5 through 6 valence electrons. They have high ionization energy. That means it's difficult to remove electrons from nonmetals. It takes a lot of energy to remove an electron from a nonmetal. They have high electron affinity, which means when they gain electrons, they lose a lot of energy. They unload a lot of the excess energy that they have, making them much more stable. In other words, gaining electrons will make nonmetals stable. This is why they are going to gain electrons. When they gain electrons, again, that's going to throw the protons and electrons out of balance. This time there will be more electrons than protons, meaning they form negative ions. The other name for a negative ion is anion. In the ionic bonding process, the metals will lose electrons, the nonmetals will take them. So we're going to see a transfer of electrons from metals to nonmetals. Let's take a close look at how this changes atomic structure. We're going to use a relatively small atom as our example. We'll talk about aluminum first. Aluminum is a metal. In group 3A. This 3A tells us it has 3 valence electrons. As a metal, it has to lose these 3 valence electrons to become stable. Let's start off by taking a look at neutral aluminum. Aluminum is atomic number 13. Has an atomic mass of 26.98. This tells us we have 13 protons, protons being atomic number. As far as the neutrons are concerned, it's going to be the mass rounded to a whole number, 27, minus 13. There are 14 neutrons. The electrons in the neutral atom will be the same as the protons, at 13. In the ion, the atomic number is still going to be the same. The atomic mass is still going to be the same. So the protons will still equal 13. The neutrons will still equal 14. But we have to lose these 3 valence electrons. We have to take these 3 electrons out of our atom. So instead of having 13, it'll have 10 in its ionized state. Again, we have an imbalance of protons and electrons. We have 13 protons giving us a charge of positive 13. We have 10 electrons giving us a total negative charge of negative 10. Positive 13 plus negative 10 equals positive 3. That is the charge that our ion has, and that charge is written in the upper right-hand corner of the symbol to indicate that the aluminum has indeed been ionized. Let's take a look at a nonmetal. Let's talk about oxygen. Oxygen is a nonmetal in group 6A. Being in group 6A means it has 6 valence electrons. As a nonmetal, it's got to gain. It's got to gain what it needs to have an octet. It needs to gain 2 more electrons. It has 6 already. When it gains 2 more, it'll have the 8 it needs to become stable to satisfy the octet rule. Again, let's look at the neutral versus the ion. Neutral oxygen. Atomic number 8. Atomic mass 16, rounded 15.999. What the table says, rounds to 16 for the calculation of neutrons. Protons are atomic number. Neutrons are the rounded mass of 16 minus the atomic number. And again, the electrons will be the same as the protons in the neutral atom. In its ionized form, Again, the atomic number doesn't change. The protons are still 8. The mass doesn't change. The neutrons are still 8. But the electrons will. We have to gain 2 more electrons to satisfy the octet rule. And when we do, we'll have 10. Again, there's that imbalance between protons and electrons. We have a positive 8 charge being produced by these 8 protons. We have a negative 10 charge being produced by these 10 electrons. Add those two together, you get negative 2, which is the charge that you see on the oxygen ion. Now let's take a look at something real quick. If we go back to the aluminum, we had 10 electrons that were in the ion. We go to the oxygen and we have 10 electrons that are in the ion. That is no coincidence. All of these elements are trying to obtain the same electron configuration as a noble gas, so they can be as stable as that noble gas. Atomic number 10 happens to be neon. Atomic number 10 means that it has 10 protons, but in its neutral state also means it has 10 electrons. By attaining 10 electrons, the oxygen and the aluminum will have attained the same electron configuration as the neon. If we look at aluminum's electron configuration with the 13 electrons that it's supposed to have, it has 2 in the 1s orbital, 2 in the 2s orbital. It's got 6 in 2p. 2 plus 2 is 4, plus 6 is 10. 3 more to go. It has 2 in the 3s orbital. 1 more to go in the 3p. 1s2, 2s2, 2p6, 3s2, 3p6. Again, we said aluminum has to lose 3 electrons. These are the 3 electrons it's going to lose. The one that's in 3p and the 2 that are in 3s. And when it does, its configuration changes to 1s2, 2s2, 2p6. The same electron configuration that neon has. Oxygen starts as 1s2, 2s2, 2p4. 2 plus 2 is 4, plus 4 is 8. 8 electrons. We're adding electrons this time. And again, we said we had to add 2 electrons. So basically, those 2 electrons are going to go into this 2p orbital here and fill it up. Take it to its max. Changing the configuration of 1s2, 2s2, 2p6. Again, exactly the same as neon. These ions are forming in order to give these atoms the same electron configuration as a noble gas in order to impart some stability on it, as is afforded to it by the octet rule.